As this video plays, please follow along and fill in the blanks in your notes handouts. If there's any additional information you would like to write down, feel free to use the lines on the right side of each slide. If you miss any information, your teacher will post access to this video on their Edmodo site. Therefore, you'll be able to replay and pause or even rewind this video at your convenience. Today we will be talking about capacitors and capacitance. A capacitor is named for its capacity to store electric charge and energy. A capacitor is two conducting plates separated by a finite distance. Each plate has a given area, and they are separated by a given distance. For the best voltage, we must have one plate that's positive and one plate that's negative. Capacitance relates the charge to the potential difference. So we will use the equation C equals Q divided by V, where C equals capacitance, Q is the charge of the plate. We will use a capital Q in this case to differentiate between a point charge of an electric field and a charge of a whole plate. And V is our potential difference or voltage. Our SI unit for capacitance is a coulomb divided by a volt, which is also called a farad. Let's try a sample problem. A 0.75 farad capacitor is charged to a voltage of 16 volts. What is the magnitude of the charge on each plate of the capacitor? First, we're going to start with a guess method, so we need to find our givens. The numbers in the problem, we have a 0.75 farad and 16 volts. 0.75 farads is the capacitance, and 16 volts is the voltage or potential difference. Our question asks us to find the magnitude of the charge. We know that charge is symbolized with a Q, so for our unknowns, Q equals a question mark. Remember that when we're talking about capacitance, we use a capital Q instead of a lowercase q to symbolize our charge. We know that our equation for capacitance is charge divided by voltage. If we rearrange this equation to solve for Q, we get that Q equals C times V. Okay, our next step is the first S, which means substitute. So we're going to take the numbers we wrote down in our given information and plug them into our equation. That gives us Q equals 0.75 times 16. When we put these numbers into a calculator to solve them, which is our last S, we get Q equals 12 coulombs. Remember, if there's ever a prefix in front of a unit, we must convert to the standard unit. We cannot leave the prefixes. That would give us an incorrect answer. There are many types of capacitors, but our simplest capacitor is one that is considered to be a parallel plate capacitor. It has two plates separated by a distance d, and they are always parallel to one another. In all capacitors, no matter the shape or size, the capacitance will increase as the plates become larger, therefore giving us a larger area, and the capacitance will decrease as the separation between the plates gets farther apart. The capacitance of a capacitor depends very much on how we make it. We know in general that capacitance is proportional to the area. Not only is it proportional, but it's directly proportional. It's also inversely proportional to the distance. In case you have not seen it before, this little symbol means proportional. And just a reminder, directly proportional means that as one gets bigger, so does the other, but inversely proportional means as one gets smaller, the other gets bigger. We will also use what we call a constant of proportionality, meaning some multiplier, to show us just how much it changes. In this case, our constant is going to be the permittivity constant. We must always know where to look up this number. It will be the same forever and always. It's 8.85 times 10 to the negative 12th. When we put all of these things together, we get an equation that says capacitance is equal to the permittivity constant times the area divided by the distance. The symbol for the permittivity constant would be pronounced epsilon naught. That epsilon is a Greek letter equivalent to E, and this is the lowercase version of epsilon. Let's try a second sample problem. Please take 30 seconds to read the question and see if you can identify the givens and unknowns. Remember that if we have an SI prefix, we must convert our units. Okay, let's see if you got what I did. I see that this question is asking for the area of a 1 farad capacitor that has a plate separation of 1 millimeter. I believe the unknown is area. Okay, and it says that we have a 1 farad capacitor, so that must be what our capacitance is equal to. And we have a separation of 1 millimeter. That must be our distance. Don't forget to convert. So that would be equal to 0.001 meters. Our equation for capacitance we know to be capacitance equals the permittivity constant times the area divided by the distance. That must mean that we also know the permittivity constant, even though it's not stated in the question. It's something we know and are easily able to look up. So we should add that to our list of givens. And our permittivity constant is 8.85 times 10 to the negative 12th. Our next step is to substitute our numbers into our equation. That gives us 1 equals 8.85 times 10 to the negative 12th times the area divided by 0.001. As we solve this problem, we get area equals 1.13 times 10 to the 8th meters squared. If we would take the square root of this number, we get that each side of this capacitor must be 10,629 meters. That's several miles long. So, is it practical to build such a capacitor? Absolutely not. So how can we get a 1 farad capacitor? Okay. The trick is going to be to reduce our area. That means we have to use less material and thus spend less money. But we still need that same capacitance. So how do we do that? The answer is to add what we call a dielectric. What is a dielectric, you ask? Well, a dielectric is an insulator that when placed between the plates of a capacitor gives it lower potential difference with the same charge. This is because the material we're going to use is polarized. This will help to drastically increase our capacitance with a much smaller area. Okay. Remember, the dielectric is an insulating material placed between the two conductors to help store the charge. In the previous example, we assumed that no dielectric was used, and thus we had a vacuum between the plates, or simply air. If we place a dielectric between the two conducting plates, that's also going to slightly change our equation. We're now going to add a K to our equation. This K is the dielectric constant. This constant will change based on what kind of material we're using. A parallel plate capacitor is constructed with a plate area of 0.028 meters squared and a separation of 0.55 millimeters. Find the magnitude of the change of this capacitor when the potential difference between the plates is 20.1 volts. In this problem, our given information, area is 0.28, distance is 0.55 millimeters, and voltage is 20.1 volts. So let's write all that in our given information. Again, area equals 0.028 meters squared. Distance, or D, remember D and X can be interchangeable, is 0.55 millimeters, which is also equal to 0.00055 meters, and voltage equals 20.1 volts. Now, this question asks us to find the charge. We know our symbol for charge is Q, so Q equals a question mark. As we look at our equation sheet, we see that there is not one exact equation to go straight from this given information to the charge. That means this problem is going to require more than one step. Remember, it's easier to take the stairs to get to the second floor than it is to try and jump in a second-story window. Okay. So the two equations that we will need Q equals C times V, but in order to find C, we will have to use C equals epsilon naught times the area divided by the distance. The next two steps of this problem are to substitute and solve. We must first substitute and solve for C, our capacitance, so that we can then solve for the charge. So, C equals our permittivity constant, epsilon naught, which is 8.85 times 10 to the negative 12, times our area, which was 0.028, divided by our distance, which when we converted was 0.00055. Okay. When we calculate all that in the calculator, we get that C equals 4.31 times 10 to the negative 10th. Now we're going to take that answer and plug it back into our other equation to solve for charge. So Q equals C times V. That gives us Q equals 4.31 times 10 to the negative 10th times 20.1 volts. And that equals 9.06 times 10 to the negative 8th coulombs. The polarization of the dielectric results in a lower electric field within the capacitor. The new field is given by dividing the original field by the dielectric constant. So if we take this new equation and substitute it into our other equations, we can simplify and solve and find that our capacitance is our original capacitance times the dielectric constant. The dielectric constant is a property of the material. Here are some examples. Water has a dielectric constant of 80.4, while a vacuum, which is just air, has a dielectric constant of only 1. A dielectric constant is different for every material, therefore you will need to know how to look it up in a table such as this. Let's say what we're trying to build will not work if we only use one capacitor. So we're going to have to use several. There's two basic ways to assemble more than one capacitor together. The first way is in a series. That means we place one right after another one. We can also assemble them in parallel, which is between a set of junctions and parallel to each other. You can see that these lines for each capacitor are parallel. What we're looking at on the right is what we call a schematic diagram, where we use symbols to represent different parts of an electric circuit. We'll study these more in depth here shortly in a few days. But first, let's look at this one just briefly. All of these straight lines represent wires. This round symbol is one of many symbols we can use to represent a light bulb, and a capacitor is represented by straight lines of equal distances. Okay. In a series setup, the wires connect from one capacitor to another, so all of our electricity must go through each capacitor. In a parallel setup, separate wires connect each capacitor to the battery. Therefore, the electricity could flow through just one capacitor and the circuit would still work. Now let's look at how the equations change when we work with more than one capacitor. When we're working with capacitors in series, each capacitor is charged by induction, so they have the same charge. The electric potential, on the other hand, is divided up amongst them. In other words, the sum of the individual voltages will equal the total voltage of the battery or the power source. So, if we plug the total voltage into our capacitance equation, we can solve and find out that the capacitance of capacitors lined up in series is equal to 1 over the capacitance of 1 plus 1 over the capacitance of 2, and so on. This is summarized in this equation with the symbol sigma, which, if you remember, means add or sum, which can also mean total. Now let's look at capacitors lined up in parallel. In a parallel configuration, the voltage is the same because all three capacitors touch both ends of the battery or the power source. As a result, they split up the charge amongst them. So the total charge would equal the charge in 1 plus the charge in 2 plus the charge in 3. If we take that and plug that into our capacitance equation, we can find that the voltage in one is equal to the voltage in all of the others. And our capacitance is equal to the sum, or total, of the individual capacitance of each capacitor. We know that capacitors are designed to store energy, and that any time we store energy, we refer to it as potential energy. In this case, we're going to be more specific and call it capacitor potential energy, which we're going to symbolize with capital U subscript C. If we plot a voltage versus charge graph, and we wanted to find the area, we would multiply the two variables according to the equation for area. We know area is base times height, so voltage times charge. If we look at our units, we know that the unit for voltage is joules per coulomb. The unit for charge is coulombs. When we multiply these, the coulombs from the charge is on top, the coulombs from the voltage is on bottom, therefore they would cancel out. And that would leave us with joules. And we know that joules in every situation is the unit for energy. Now let's find the area under the slanted line. This area is a triangle, and that would give us 1/2 voltage times charge. Okay, this area is referred to as the energy stored inside a capacitor. Note, the slope of this line is the inverse of the capacitance. Okay. So we can take this energy equation that we just found from this graph, combine it with our capacitance equation, and rearrange to find many different forms of this equation. This one should look familiar to two energy equations that you've already seen. Remember, kinetic energy was 1/2 mass times velocity squared, and elastic potential energy was 1/2 times the spring constant times the distance squared. We have all seen medical shows where a patient is zapped with the paddles. Those paddles are part of what's called a defibrillator. In a typical defibrillator, a 175 millifarad capacitance is used. There's a potential difference between the plates of 2,240 volts. So, let's figure out what the charge is on each plate. Given we have potential difference or voltage equals 2,240 volts, and capacitance equals 175 millifarads, which is equal to 0.175 farads. The unknown in this problem is charge. So we're going to say capital Q equals a question mark. We know that our equation for charge is Q equals C times V. Now let's substitute our numbers into that equation. We get Q equals 0.175 times 2,240. When we plug those numbers into a calculator, we get a charge of 392 coulombs. Now let's find the energy stored in a charged-up defibrillator. In this part of the example, our unknown will be U, our potential energy. Since we already know Q, C, and V, we may use any of the three equations we have to find potential energy. Each has their pluses and minuses. I personally, in this situation, would use the green equation, potential energy equals 1/2 times the capacitance times the voltage squared. I would use this equation because what if we made a mistake calculating our charge? In that case, we would end up with another wrong answer if we used any of the other two equations. However, I know that information they gave me in the problem is correct, so I personally would choose this first equation. Although the second and third equations are also very easy to work with. Please take 30 seconds and use the equation of your choice to solve this problem. Capacitors can be very helpful in many different situations. The energy stored inside them is useful in camera flashes, cardiac defibrillators, and many others. Almost all electronic devices used today rely on one, if not more, capacitors. If we divide the stored energy by the volume of the capacitor, we can find the energy per unit volume. This result is valid for any electric field. So we get that 1/2 times epsilon naught, which was the permittivity constant, times the electric field squared is equal to the energy density. One other thing to keep in mind about capacitors is that if the electric field in a dielectric becomes too large, it can tear the electrons off the atoms, thereby enabling the material to conduct. This is called dielectric breakdown. The field at which this happens is called the dielectric strength. The dielectric strength is different for every kind of material, just like our dielectric constant was different for every kind of material. That's all for these notes. Remember, if you missed any information, your teacher will post access to this video on their Edmodo site, and you are more than welcome to watch it as many times as you would like.